magenta line inside there, which is the smooth value of all the measurements. Signal to noise ratio, 20 some dB, but that's really wrong. We need to it's a little higher than that. And so the signal to noise ratio you can see here as the beam is scanning. And here you see the off-nose error magnified by 10, because otherwise you wouldn't be able to see it. And here you see blow-ups of different things. This is therefore the scan loss. This is that picture blown up. And you can tell that the antenna wasn't centered when this was done. Typical scan loss is about 4.5 dB if you average the two. Over here you look at what happens at the transient when the pedestal stops. You have this huge antenna and it's stopping, and so there's some of this compliance going on, pedestal compliance. And so you get the track and you can see the smooth thing, you can see the smooth trace tracking the actual measured data pretty well. The effective loss, when that happens, is the tracker is starting to keep up with a sudden change in dynamics, as you might see when you launch a vehicle or you, something blows up but you still have the telemetry pack intact, is a very slight reduction in signal strength of just about a dB. The off-nose error is magnified by 10, is about 4/10 of a degree before the tracker realizes that something has changed and it updates itself. And it updates itself based on error, so the points are a lot closer spaced when the error gets large. The DMOD and bit sync, again, I'm jumping through because I'm going to be running out of time very soon. The DMOD and bit sync is, the hardware is complete, the firmware has been simulated, and is almost complete. It's being programmed. The up converter is under test right now. There's extremely tight digital filtering, and you saw an example of that before, to match the information bandwidth. There's the analog demodulation, AM and FM we provide between 30 kilohertz and 20 megahertz. Digital demodulation between 10 kilohertz and 30 megahertz, which is the information bit rate could be higher depending on the modulation scheme. Basically, there's a set of PLLs that synchronize to the symbol, and we resample the data. We're using 5 samples per symbol using the Faro resampler. There is a shape recognition least squares algorithm to recognize the different shapes for the different symbols, and that feeds back a fit quality number back to the PLL to synchronize the exact timing. That's how the bit sync happens. The features that are extracted are basically sets of coefficients which are used to decipher PCM-FM, QPSK, and differential QPSK, of which SOQPSK is a subset. And then also that same information can be used to decipher multi-HCPM modulation schemes that are in the ARGM arsenal. So a true bit MATLAB model of this has been made. It's verified it does work. The FPGA coding is in process. The development team is spread across the country. The customer is in Florida. We have Malibu Research, who's built the antenna hardware and is also the prime on this, who's involved with the system concept. We have Creative Digital Systems, which is us. We are actually, at this point, acting as system engineers and making the whole system work. Pentec provided the digital acquisition and signal processing hardware, is in New Jersey. We are in Southern California. And Reka Consulting Group, which is providing the IP for all of this, is in Rhode Island. Zergo Technologies providing the LNB in Southern California. Software 6, which is providing the software, also in Southern California. It's quite a task to coordinate all these entities together. So this was done extensively through simulation, and the current status slide is really intended to show the simulation elements that have been filled in. There's also a big one here, the multipath channel, which is something that we really struggle with to emulate well. The reflection coefficient is dynamic based on various C states. The antenna aperture therefore is able to handle these things in the combiner. All these elements have been simulated. Everything in green has been actually built and tested. The stuff in the striped blue has been built, but is under test, and the stuff in the white, the hardware exists for and is actually being programmed. This is also this is what keeps the beam on the target. There's radar signal processing and target acquisition techniques have been used. It's extremely robust and very fast. Soon we will be ATPing the system, hopefully in late January, installing it in the aircraft at Kimball Air Force Base soon after that, and there'll be a fly-off against the legacy system in April or May of '07, and hopefully we'll keep you posted on what happens there. So basically, to summarize and possibly leave some questions that there might be, we believe that digital beamforming is here to stay. The challenges have been massive synchronization, rapid application development techniques for software. We have the whole system available through simulation and emulation, and as the hardware happens, you compare it against the simulation and emulation to make sure the hardware works well. The data processing approaches are unique now and are no longer constrained to processing power, because at this point the processing power has exceeded pretty much whatever you can do because of FPGA density. Current system target capacity has been doubled. We're lower weight, comparable power. We use a little bit more power than the legacy system, but it's comparable. And we hope that this is a flying test bed for development for multipath algorithms, which I'm sure it'll be able to support. So here we are with digital beamforming, and I believe we can support LNS band telemetry at this point. That was quick. Lots of design notes, which I won't be able to share with you. There's a nice one where mutual coupling is happening and modeling is going on. But I'm going to stop now and ask if anybody has any questions.